Hello and welcome back. I've got 5 minutes until day 5 drops. I don't think I'm going to make it, but let's go over day 4. Okay, so for day 4, we get our input as a grid. There's two symbols on here. There's a dot that represents empty space, and there's some @ signs that apparently represent paper rolls that are going to be hauled by a forklift. Our job is to determine paper rolls that have fewer than 4 rolls of paper in the 8 adjacent positions. So you can kind of think of like around each one of these @ symbols, we'll draw a little box. And if there are fewer than 4 other rolls of paper immediately surrounding it, then we count those. And for part 1, we just have to do that once. And we add up all of the rolls of paper that fulfill that criteria, and we get our answer. For part 2, it's a little more involved. We have to basically keep doing that process. So we do it once, we do it twice, et cetera, et cetera. We basically keep going until there are no rolls of paper that fulfill that criteria. And then at that point, we count up the total rolls of paper that were removed, and we add all those up, and we get our answer. So just right off the bat, this is sort of similar to like a cellular automata type of problem. APL is pretty famous for having a very concise solution to like game of life. So this should be right in our wheelhouse. We will work with the test data at first and get test.txt1, and we get our data. Because it's a grid, we can just mix it into a character matrix, and then we can turn it into a Boolean matrix by matching on the @ symbols. So all the ones here in our Boolean matrix signify a paper roll, and we will assign that to P. Okay, now in APL, and I've used this in previous videos, but there's a very handy primitive for these type of cellular automata-ish problems, and that's stencil. Stencil basically breaks an array into subarrays. It kind of does like a sliding window type of thing. And then you can do operations on those subarrays independently. So in our case, if I do something like close omega key, you specify the size of the window that you want. So we want a 3x3 matrix, and we can apply this to P. And this kind of shows you how the sliding window will go and like the different subarrays that are generated. You'll notice that, so like, it starts centered on the corner, and it fills in the out of bound areas with 0. I don't think you can change this fill element in stencil, which is a shame, but the default of 0 works for our purposes very nicely. And so we just get a sliding window, and then we can we can basically count how many paper rolls are in each window. Now there's a slight problem, which is that if we take a look at this subarray, oh, don't change on me. Oh, well, I guess, okay. If we look at this subarray here, we have a 1 in the middle, which means that it is a paper roll, and then we have 3 paper rolls surrounding it. What were the criteria? Was it less than 4? So 3 should be good. The problem is if you add all these up, it'll equal 4. And the reason is that you're counting the fact that it's, there's a 1 in the middle signifying that it's a paper roll. But we'll take care of that. Okay, so let's do this. Let's just do right tech stencil 3x3 on our input, and this will give us a big old flat array of rank 4. 3x3 is on the end there. We want to be able to add all the numbers in the 3x3 matrices, so we can ravel mark 2, and that'll give us an array of this shape. And now we can reduce sum on the last axis to get the total count of paper rolls within each subarray. And because it's counting the paper rolls themselves, we're going to do 4 greater than here. So this gives us basically all the spaces that won't be moved in the current iteration. This is a little bit counterintuitive, but then if we do like p minus here, right. We also have to do p and. So this is how we, so if we look at, we'll just do this again. If we look at our input, we already have ones that signify all the paper rolls. And here we could be counting spaces that aren't paper rolls, right? So if we do an and against our output here, then we just get the paper rolls that are. Wait, is this right? I think. Hang on. Sorry, let me do 4 less than. There we go. So I got a little mixed up, but the plan is basically, so we're going to figure out the paper rolls that remain instead of singling out the paper rolls that we want to remove. And that's a little bit counterintuitive, but it works very well for our part 2 answer, which we'll get to in a second. So these ones are all the kind of like spaces that would remain, right? But this also marks a lot of spaces that are not paper rolls. So this is where the and comes in, right? And now this matrix here represents the paper rolls that are left after we do a single removal operation. And now we can get the paper rolls that were removed by taking our original inputs and subtracting the input that we generated. So now this matrix represents all the paper rolls that are getting removed in this iteration. And if we ravel that and we sum it, we get an answer of 13. So we would think that there are 13 paper rolls to be removed in this first iteration. And for the part 1 test input, that is correct. Okay. Now for part 2, we basically just have to like iterate this function, right? So let's, first of all, what if we just, so we'll turn this part into a function and we'll say omega, omega. And then if we run it on our inputs, well, we need the answer summation part. We should get the same answer. Yep. So let's call this function f. And we're going to be using the power operator. I use the power operator a lot. You can feed it a number, in which case it'll do a given number of iterations. I think I used this actually in my, was it day 3 or day 2? It's all kind of a blur, but there was one where I had to do like I think it was day 3, where I had to do like a certain number of iterations. But the other thing that you can do with the power operator is you can feed it a function, and it will keep running until the previous input and the last the generated input, basically the input after like running the function. It will keep running until the function parameter that you supply to the power operator returns a true value, or like 1. And in our case, we can just run this until it matches on our input. And this gives us all of the, so with power match, it's basically running the function until the input converges. So on the last iteration, we ran the function and there was no difference. So this should be the, this should be our part 2 answer if we do the same sort of subtraction and summation of 43. which is our part 2 answer for the test input. Now, if we wanted to get really fancy with this, we are kind of like duplicating our answer summation logic here. So we could wrap this in another function that takes care of that for us, so we don't have to type it out for both answers. The problem is how do we differentiate the behavior of the power operator between part 1 and part 2. And we can do that by making our function here an operator. This double @ sign basically means that when we call this function, it expects to have some other function parameter on the left. You can think of this as higher order functions or whatever's convenient. And we can run that on our input. And now for part 2, we should be able to just do f on our input, supplying the match primitive, and it works. For part 1, we can be a little cheeky and use the not match. So this will succeed on the very first iteration because the input that we supply and the output of the function that we're running will be different on the first iteration, and we get an answer of 13. So this kind of thing where you define your own sort of like higher order functions can be very useful. I mean, in this case, we're saving, I don't know, what is this, 5 characters between part 1 and part 2. But it's kind of cool, and it certainly can be useful in larger problems. So let's see. So this is what all of that looks like. 4 lines, day 1 and day 2. And if we run this on the actual inputs, we get 1587 and 8946, which is the correct answer for part 1 and the correct answer for part 2. Now, I'm not going to say that this one is the most efficient solution. Our part 2, because it has to do so many iterations, and because stencil is not really very efficient, takes quite a while relatively. It takes a second to spit out the answer. And someone on Reddit, is it Peter or Peter, pointed out to me that stencil, first of all, like as a baseline, it's not super efficient, but you can make its efficiency even worse if the function that you're supplying to stencil does a lot of work inside of it. So like we could, we're operating on the arrays that it generates, but like we could do all of this within the stencil operator. So that would look like for less than something like this. And now we're basically applying this function on every subarray. And this is much slower. Let's see if we get the right answer first. Takes a lot longer. We do get the right answer. And this is going to take even longer because CompX has to run it multiple times to get an average runtime. But basically, the lesson here is, almost 5 times longer. So the lesson here is that when you're working with stencil, just be careful in general because it's not the most efficient thing out there. But then when you do use it, just try and keep your functions as simple as possible. And I think probably, I haven't looked, but I would bet that there's some idioms here that the Dyalog interpreter kind of optimizes. So in APL, idioms are basically like, I don't know all the technical details. I think the interpreter will kind of like scan ahead a couple of characters, and if it sees certain patterns, it can do more efficient calculations that don't involve like materializing a bunch of intermediate arrays and things like that. I mean, cellular automata types of problems and stencils, the stencil operator go together like peanut butter and jelly. Sorry for my non-American viewers. But yeah, this is the whole solution. 4 lines. Um, and now we'll get cracking on day 5. But yeah, thanks for tuning in.